Okay. All right. Before starting, I just want to remind you we're set for our second exam for this Friday. Syllabus is posted on the web as our sample tests. Okay. You have any questions you want to ask? All right. So today we're going to start looking at what you might call the analog of radix sort to the search problem. We look at different ways of organizing dictionaries. So far, the dictionary organizations we looked at, whether it was binary search trees or higher order search trees, were based on making full key comparisons amongst the search key and the items currently stored in your dictionary. The structures we want to explore now are those where the organization is based not on the full key, but on parts of the key. So you do a decomposition of the key using some radix, like you would in a radix sort. And initially, what you're going to be looking at is decompositions using a radix of 2, so binary decompositions of keys, and then organizing search structures based on the bits in a key. Okay, so as I said, it's an analog of radix sort to searching. We'll interpret each key as being a string of bits. So you got zeros and ones. And we may be dealing either with fixed length keys. So for example, here, all of the keys are 4 bits long. Or you may be dealing with a situation where the keys are of variable length. So some keys may be short and some may be long. Okay. And most of our discussion will be centered around, at least today, around fixed length keys. And part of it will make some reference to variable length keys as well. Okay. The dictionary is organized using, say, the bits in a key. Find a fair amount of application. One particular application area where a large number of variants of the fundamental structure we're going to look at today have been developed and are in commercial use is in the implementation of router tables for packet forwarding in the internet or for packet classifiers and firewalls. So I guess sometime next week we'll have a lecture where I'll just kind of review the application of tries to packet forwarding and packet classification applications. Okay, but we'll see the details of that next week. Okay. And when we get there, we'll see that if you're dealing with IP version 4, then the keys will be variable length going up to 32 bits in length. And if you're dealing with IP version 6, the keys would be variable length going up to 128 bits. Okay, okay, so binary decomposition of keys actually gets used quite a bit in practice. We'll also look at decompositions using higher radixes than 2 in a subsequent lecture. All right, so let's start by looking at probably the simplest type of search structure based on key decomposition. This will be a digital search tree. And then we'll take a look at an alternative to a digital search tree, something called a trie. Okay. All right, so in a digital search tree, okay, it's a search tree, and if it's not empty, then one of the pairs of a dictionary resides in the root. You can place any one you like out there. And the remaining ones get partitioned into the left and right subtree depending upon their first bit. Okay. So if the first bit is a 0, then those pairs will be in the left subtree. And if the first bit is a 1, they will go into the right subtree. Okay. So the partitioning into left and right subtrees isn't done by comparing the entire key with what's in the root, but only by looking at the first bit. So if the first bit is a 0, you go into the left subtree. If the first bit is a 1, you go into the right subtree. And then the left and right subtrees are similarly organized. Okay. Right, the best way to get a feel for that definition is to simply look at an example. Okay. All right, and we'll actually build the example as a sequence of inserts starting with an empty digital search tree. The number of nodes in a digital search tree will be exactly equal to the number of entries in the dictionary. So when you start with an empty tree, we got no nodes. And then we're going to insert a pair whose keys is 0, 1, 1, 0. This would result in a one-node search tree, and that one-node search tree will have a dictionary pair in it, the single one that's in the dictionary. So you just end up with that. Okay. Right, now suppose you want to insert the key 0010. Okay. So the first thing we'll do is we'll search for the key. Okay. So we have only one node, so I'll look at the key in this node and find that they're different. Okay. So it's not a duplicate. To put it into the tree, I will look at its first bit, which is a 0, so we'll have to put it in the left subtree. Okay. And since the left subtree is empty, there's nothing to search there. We just get a new node and put that in over there. So we end up with this structure. Okay. All right, now suppose you want to put in a 1001. Okay. So you start at the root, you make a comparison. Okay. They're not the same. Okay. To decide whether to go to the left or the right subtree, when you're at the root level, you look at bit 1. Okay. The leftmost bit, which is a 1, so I go into the right subtree. The right subtree is empty, so that's where you make the insert, and we end up with that structure. All right, now suppose we want to insert a 1011. Okay. So you start at the root, you compare, they're different. Then you look at the first bit, it's a 1, so we end up here. Okay. You compare the two, they're different. At this level, you look at bit 2. The second bit out there is a 0, so we'll go down here. You fall off the tree, that's the place to make the insert. Okay. All right, suppose you want to insert 4 zeros. Okay. So you start at the root, you don't get a match. So you look at the first bit, it's a 0, you end up here. You compare the two keys, they're not equal. So you get the second bit from there, which is a 0, and you go into the left subtree here. Okay. Since it's empty, you know that 4 zeros is not currently present, and that's the place to insert the new pair. Okay. So in a digital search tree, the root can contain any one of the dictionary pairs. The remaining pairs are partitioned depending upon the first bit. If it's a 0, you come here. If it's a 1, you go there. Okay. At this level here, the partitioning will be done based on bit 2, then on bit 3, then bit 4, and so on. Okay. All right, so if you want to search a digital search tree, as I said, you start at the root. Okay. You compare the search key with what's in here. If it's equal, you're done. If it's not, you look at bit 1. If it's a 0, you go there. Otherwise, you go to the other side. And you kind of repeat that process at each level. We saw how to do an insert. You basically do a search, and then wherever you fall off, you insert a new node with the new pair. If you want to do a delete, okay. So suppose you want to delete the item in the root. Okay. So to delete the item in the root, you have to find a replacement for that item. Okay. And you have to get a replacement in such a way that you don't mess up the partitionings at the remaining levels. Okay. At each level, your elements or pairs are being partitioned by a particular bit. So a suitable replacement for this fellow here would be anybody who's sitting in a leaf below it. Okay. So if I took the 4 zeros and put it up here, then I could throw this node away, and I would not affect the level numbers of any other node. If I took this fellow and put it up here, I could throw the leaf away. Okay. Now, some things that don't work, for example, is if you're trying to remove, let's say this one, 1001, okay, then if you just change the pointer from here to here, okay, and assume for a moment there are subtrees down here, you will end up with a problem. Okay, because the partitioning here into subtrees was done previously by level 3, but by promoting this up to level 2, the partitioning is now done here by bit 3 rather than bit 2. Okay, so you would have a problem. Okay, so when you do a delete, you need to go down until you find a leaf, find the item in the leaf, move it up to where you've got a vacancy, and then throw away that leaf. Okay, so it's not quite the same as deletion from a binary search tree. Okay. All right, the time required to perform any of the 3 operations, search, insert, and delete, depends on the number of bits in the key. It's linear in the number of bits. Okay. So if the number of bits is small, this is a good way to go. If the number of bits is large, this isn't such a good way to go. Okay. All right, any questions about digital search trees? Yeah.
During insertion, what if left and right nodes are operated at certain level and the bits to be compared in the key are exhausted and we go down?
Right, so the question is what happens if the bits in the key are exhausted and you still haven't fallen off the tree? Okay. The assumption we made was that all keys are of the same length. Okay. And when all keys are of the same length, that case cannot arise. Okay. So that's the reason to make that assumption that all keys are of the same length. Okay. Now there's a way around it, and we'll see that I guess when you look at variants of the structure, where you make provision to hold different kinds of elements in the interior, or you take a key and at the end you put in a special digit. So then you really increase the radix by 1. Okay. So we may take binary keys and suffix them with a special symbol, say a pound symbol. Now you cannot have one key which is a proper prefix of another, and that prevents the case that you mentioned. Okay, but we'll see that later when we look at higher degree tries. Okay, so under the assumption that all keys are of the same length, the insertion algorithm always works the way I described. If the item is not there, you will always fall off the tree before you run out of bits. Okay, other questions? Okay. Now, in this scheme, okay, when you're doing a search or any of the other operations, you make one comparison at each level. So you compare the key stored here with the search key. So the total number of key comparisons is also of the order of the number of bits. Okay. Now, this makes the strategy in its present form not very efficient when you're dealing with long keys. Okay. Because then the key comparisons are expensive, even though you're doing a small number of them, each one is expensive. Okay. All right, so people came up with alternative structures, which are also based on this radix decomposition idea, where the total number of full key comparisons that is needed is limited to 1. Okay. So let's take a look at those alternative structures. The simplest is a binary trie, and then you can go to higher order tries and variants of higher order tries that we'll look at later. Okay. Right, so the word trie was derived from the word retrieval. The structure was initially designed for information retrieval applications where people were indexing large texts. So maybe you're indexing articles in a magazine and they could be thousands of characters long. So you didn't really want to be comparing 1,000-character keys at each level of the trie, of the structure. Right, the nice property about these is you can perform your operations by using at most one comparison. Again, we'll assume our keys are all of the same length, but as we'll see later, that's really not a hard requirement. We can relax that to accommodate variable length keys. Okay. So when you're dealing with fixed length keys, we'll have two types of nodes in the system. One is a branch node, and a branch node has a left child and a right child pointer, okay, but no data fields. Okay. So that's different from a binary or a digital search tree where the nodes had both left child, right child, and a data field. Okay. So here a branch node cannot store data, it can only have pointers. Okay. Then you have element nodes, where element nodes can't have children, okay, but they can only store data. Okay. All right, so the fixed length case, we will have a node structure. You have really two types of nodes, branch nodes and element nodes. All right, let's look at an example. Okay. All right, so the green nodes here are the branch nodes, okay, and the yellow ones are the element nodes. The dictionary pairs or keys are divided out again by looking at the bits. Okay. So at the root level, you look at the first bit. If the first bit is 0, it's going to show up on the left side. If the first bit is a 1, it's going to show up in the right side. If you have more than one dictionary pair in a subtrie, then again you partition, but now we're going to do here with bit 2. So if it's a 0, you come here. If it's a 1, you go there. Again, if this subtrie has got more than 2 pairs, you'll partition. If it's a 0 in bit 3, you come here. If it's a 1, you come there. Okay. So the partitioning goes on till you're left with a single pair, and at that time you put in a data node. Okay. Right, we might call this a pure trie. In practice, people will not do this partitioning all the way down to single entities or single pairs. You may stop the partitioning when you reach a number of pairs that may be, say, 5 or 10. Okay. So you have the concept of a bucket, and once the number of pairs here is small enough that it fits into a bucket, you stop the partitioning. Okay. If you look at a search, okay, so suppose you're searching for a 0011, okay, well then you start at the root, okay, you look at the first bit, it's a 0, so you come here. You look at the second bit, it's a 0, you come there. You look at the third bit, it's a 1, you come here. Okay. So once you reach a data node, then you have to do a compare to make sure there is a match. Because you could come here for any key that begins with 001. So even if it had been 0010, it could have been stored here. Okay. So you follow a path dictated by the bits in your search key, and that path would either fall off the trie. So for example, if you're looking for something that begins with 01, you'd fall off here, in which case no comparison is done. Or the path will end at a data node, in which case you have to compare the search key with the key stored there to see if there's a match. Okay. All right, so searches can now be done with at most one comparison, whereas the previous structure, digital search trees, required a number of comparisons that was equal to the number of bits. Okay. All right, if you have variable length keys, then I will use a single node type, okay, which could have, say, left and right child fields, and each node will be able to store two pairs, okay, a left pair and a right pair. And the strategy I will use is that the left pair will have a key that terminates at the root of the left subtree of this node. Okay. Or if the left subtree is only going to contain one pair, then I'll stop here, I won't do any further partitioning. Okay. Similar strategy for the right pair. Okay. Again, it's probably easier to look at an example than to try and follow the wording of the thing. Okay. All right, so here, I guess I've got two fields in a node. This, I guess, color is not showing up too good. So I've got a yellow field, that's the left one, and then I've got a light blue field, that's the right one. Okay. So at the root level, I can store pairs whose keys are 1 bit long. Okay. So if the key was 0, the pair would be stored as the left pair. If the key was 1, it would be stored as the right pair. In this case, I don't have a pair whose key is 1. Okay. At the next level, I can store pairs whose keys are 2 bits long. Okay. So on this side, the first bit would have to be 0, and then this node would have a 0, 0 pair and a 0, 1 pair. Okay. An exception is if there is only one pair to go in the subtrie, then I'll just store it here instead of going down 1, 2, 3, 4, 5 levels to store it. Okay. So I have a provision to store early in case there's only one pair left in the subtrie. Okay. Again, here, this node is nominally for keys that are 2 bits long. Okay. They have to begin with a 1, so nominally you'd put a 1, 0 here and a 1, 1 here. Exception being that if that subtrie is going to have only one key, then you might as well store it here instead of having a long path where you're trying to partition that single key further. Okay. All right, so this would be one way to handle keys of different length in a binary scenario. Again, you would search these in a similar fashion to the previous structure. Okay. So you'd follow the bits, and the last node you see on the path, take a look at the content, do a compare. If it matches, you're okay, otherwise it's not in the tree. Okay. All right, any questions about the fixed length or the variable length trie? We'll take a look at insert and delete from the fixed length in a moment. Yeah.
The yellow nodes represent the index of do they represent themselves as index?
What do you mean as an index?
Like in blue node you have the actual content and the yellow ones are the index.
Well, actually both this thing is just one big node. Okay. So the yellow part represents the left data, and the light blue part represents the right data, and then you have two child pointers, a left child and a right child pointer. Okay. So this could, I mean, if you didn't have, these fellows here, okay, then this thing here could have kept a 0, 0, 1, 0, 0 just as well, if there were no other fellows that began with 0, 0. Okay. So the partitioning strategy is, again, you look at the bits left to right, and if you're left with only one pair, then you store it in that node instead of continuing to partition a singleton. Okay. If you're not left with one pair, then what you can store at a level is determined by the length of the key. So at level 1, you can store keys of length 1, then length 2, length 3. Okay. All right, other questions? Okay. All right, let's go back to the fixed length case and look at how you would do an insert. Okay. All right, suppose you want to insert 0 followed by 3 ones. So we'd follow a path from the root. Okay. First bit is a 0, so you go into the left subtree. Next bit is a 1, so we fall off over here. That tells us that I don't already have 0, 1, 1, 1 in my dictionary, and that the place to insert it would be out here. Okay. All right, so this insert required no compares. Right, next let's insert 1, 1, 0, 1. Okay. So again, you start at the root. The first bit is a 1. The second bit is a 1. And you reach a data node. So you compare the keys and we find they're different. Okay. So to find the place to make the insertion, I need to continue to compare these two keys together. So I got a 1, 1, 0, 1 and a 1, 1, 0, 0. And I need to find out where they differ. And up to that point, I'll have to introduce branch nodes. Okay. Okay, so I put in a branch node there because now the subtry that is rooted here is going to have whatever it had before plus this 1. Okay. And before it had 1, now it's got 1, so you got 2, so you're going to have a branch node. So at that level, you're going to branch at bit 3. Bit 3 for both of these guys, 1100 and 1101, is a 0. So you don't end up partitioning. Okay. So now I'm going to have a branch node at level 4 where I'm going to branch looking at bit 4. And bit 4 for the old fellow is a 0, so it'll show up in the left subtry. And for the new fellow, it's a 1, so it'll show up in the right subtry. Okay. So this is where the sets break down into size 1 each, and you put in yellow nodes. Okay. Right, so this case needs one comparison. All right, so any questions about an insert? Okay. You perform a search. If you fall off the try, you insert a new node, a data node there. If you reach a data node, you have to do a compare, and that could involve inserting a bunch of new branch nodes, one per level. Okay. All right, the total time for that insert, of course, is limited by the number of bits. Okay. So it's the order of the number of bits in the keys. Let's take a look at the delete operation. All right, suppose you want to delete a 0 followed by 3 ones. So you first search for it. Okay. First bit is a 0, you end up here. Second bit is a 1, you reach a data node. You compare the keys, you find there's a match, so you got to get rid of this fellow. Okay. All right, so that data node disappears. And when that data node disappears, you got to decide whether its parent, if there is one, okay, this branch node here, is that a legitimate branch node, or should that also disappear? Okay. Now this branch node should disappear if its other subtree has only one data node in it. Now, if this subtree had only one data node in it, then the sibling of the node you threw away would be a data node. But it's a branch node, which tells you there's more than one down here. Okay. Every branch node is the root of a subtree that has at least two data nodes in it. Okay. So in this case, this fellow is going to stay because the sibling of the yellow node that went is a branch node, telling you that there are at least two people here. And so you got to keep that guy. Okay. Let's try another delete. All right, so this deletion took one comparison. You reach a data node, you have to compare. Well, suppose you want to delete a 1100. Okay. So you follow the search path 1100, you end up here. Okay. You do a comparison. Okay. You find a match, so you get rid of that data node. And now you got to decide whether this branch node stays or goes. Okay. To make that decision, you look at the other child or the sibling or the fellow who went. That's a data node, which tells you if you left this fellow here, it would be the root of a subtree that has only one data node in it, and that's not legal. Okay. All right, so this fellow's got to go. All right, then you back up here. Now you got to decide whether this fellow's got to go. Okay. Now, if this fellow stays, the subtry down here is going to have only one data node in it. The subtry down there is empty. So the subtry rooted here is going to have only one data node, and so that node has got to go as well. Okay. Now, if this fellow had a non-empty child, well, then this node would stay, because you'll have one fellow on this side and some number here, one or more on that side. Okay. But since you have an empty subtry to the right, this branch node here has got to go, since it's now going to be the root of a subtry with only one yellow node in it. Okay. All right, so that fellow's got to go as well. Okay. So now I'm going to ask the question whether this green node has got to go. If this one stays, you'll have one yellow node here with this guy in it, and then you'll have this subtry down here, which has one or more. Well, since it's a branch node, there are at least two people down here. Okay. So this green node has got to stay. Even if you had a yellow node here, that green node would stay, because then you'd have one yellow node and one, so this subtree would have two yellow nodes. All right, so that fellow's got to stay. We just put it in there. All right, so when you do a delete, you follow the search path, and if the item you're looking for is actually there, you'll end up at a data node. You do a comparison, and it'll be a match. We'll throw away that data node. Then you have to retrace a path going back up toward the root, looking for these branch nodes that need to be thrown away. Okay. A branch node is going to get thrown away if its other child is empty. Okay. Right, so we back up some number of levels, throwing away branch nodes as necessary. Total time required is, again, linear in the number of bits in the key, and you make at most one comparison. Okay. All right, any questions about a delete? Okay. All right, let's take a look at join. And then the split operation we'll take a look at in the next lecture. All right, so for the join, if you recall, look at a three-way join. You're given a dictionary of small keys, a dictionary of big keys, and an intermediate key. So everybody in S is smaller than M, and everybody in B is bigger than M. We want to combine these three entities into a single dictionary. All right, so the strategy that we're going to adopt is we're going to first really convert it into a two-way join. by getting rid of that middle key. Okay. So I'll take that middle fellow M and I'll insert it into the big tree and end up with a new big tree B prime. Okay. Well, so that'll take me time equal to the number of bits. Okay. Now, if my small tree is empty, then I'm done. B prime is the answer. If my small tree just has a data node in it, so if the root is a data node, I'll just take that data and insert it into B prime. Okay, and then I'm done. Okay. So the time is still order of the number of bits, it's just 2 times number of bits. You did one insert here and one insert out there. Okay. Now, if B prime is an element node, which means that B was empty, okay, well, in that case, I'll just take that element M and instead of, I'll insert it into S. Because you can organize this different, you could probably check out here. If one of the two is empty, insert M into the non-empty one and you're done. Okay. Basically, all of this stuff here is to take care of, is to one, reduce the three-way join to a two-way join, and to take care of the case when one of the two trees, S and B, is empty. Not empty, but has a, it could be empty or it has only one element in it. Okay. And if you're not done as a result of these, then when you get down here, you're guaranteed that the root of both S and B prime is a branch node. Okay. So the first 4 steps are to eliminate all the simple cases, and then if you get to the 5th one down here, both S and B prime have a root that is a branch node, which means they both have 2 or more keys in them. Okay. All right, so let's look at that situation. Okay. So now both S and B prime have a branch node as the key, as the root, and we'll break this thing down into 2 cases, depending upon whether S has an empty right subtree or it doesn't. Okay. So if the small tree has an empty right subtree, okay, so it looks like this, okay, that side is empty, and we're trying to join it to B prime, okay, and B prime may have an empty left subtree or it may not. Okay, it may have an empty right subtree or it may not, doesn't really matter. But the key thing here is that S has an empty right subtree. Okay. So the result of joining these 2 fellows when it looks like this, okay, is this try here. The right subtree is going to be C. Okay. C's got everything that begins with a 1. Nobody in B begins with a 1 and nobody in A begins with a 1. So C is going to be unchanged as a result of the join. And then what you're going to get down here would be the stuff that's here plus the stuff over there. But since everybody here, or in this whole thing, is smaller than everybody here, it follows that everybody here is smaller than everybody there, because they both begin with zeros. Okay, so we can recursively do a 2-way join for A and B, tries of a smaller height. All right, any questions about this case? Yeah. All right, in this case, the assumption is that the small tree has an empty right subtree. Okay. And so it has a left subtree A. Everybody in A begins with a 0 by definition of trie. the big tree B prime has subtrees B and C, one or both of, well, both can't be empty, but one of them could be empty. It doesn't really matter. Okay. So when you're doing the join, we say the result of the join is you're going to have a root node, which is a branch node. The right subtree is going to be C, because the right subtree is going to have everybody that begins with a 1, and it's only the fellows here that begin with a 1. The left subtree is going to have everybody that begins with a 0, and those are contained in A as well as B. So I'll do a recursive join on A and B. Okay. And I can do a recursive join on A and B because since everybody in S is smaller than everybody in B prime, and everybody in A begins with a 0 and everybody in B begins with a 0, it follows that if you forget about the 0, then everybody in A is smaller than everybody in B again. Okay. Because once you go down one level, you lop off one bit. Okay. So it's still true that everybody here, if you disregard the leftmost bit, everybody here is smaller than everybody there. And so you can make a recursive join with one bit less. And sure, once you come here, you again have to check all the cases I had before where where the root of, this fellow's root may be a data node. Okay. In which case you could just take that item and insert it into B and so on. Okay. All right, so let's look at the second case is where S has a non-empty right subtree. Okay. So if S has a non-empty right subtree, that means it's got some keys that begin with a 1. Okay. So if it has some keys that begin with a 1, then B prime cannot have any keys that begin with a 0. If B prime had some keys that began with a 0, then everybody in B would be bigger than everybody down here, but that's not possible since everybody in this whole tree is smaller than everybody in that whole tree. Okay. So if the right subtree here is non-empty, the left subtree here has to be empty. Okay. So it's got to look like that. And you can handle this in a symmetric fashion to what we had before. Okay. So the left subtree of the join will just have the left subtree of S, and the right subtree of the join, you do a two-way join between B and C. All right, so each time you make a recursive call, you go one level down the trie, and the number of levels is the number of bits. So the time required is also linear in the number of bits, okay, or linear in the height of the trie. Okay. All right, any questions about the join? Okay, so we'll stop here, and then in the next lecture we'll take a look at a split, and we'll also look at things called compressed binary tries, where we will get rid of these branch nodes that have only one child. Okay.